Hello students. This is the first in a set of videos where we are considering free fall problems. We won't actually be solving any problems in this video. Just want to spend a little bit of time talking about free fall, what it means, and how these problems can be a little bit different than your standard motion problems. You probably noticed in motion worksheet 3 that there are a set of motion problems, 14, 15, 16, and 17, that are designated as free fall problems. And they are separate from the other motion problems on the worksheet. They don't really need to be separate. The thing about free fall problems is that they're actually motion problems, just like the other problems, and they're solved using the same variables and the same equations. They really don't have to be separate from those other problems. But the thing about free fall problems is when you read through the description of the situation, it seems like some information is missing. And so at first, at least, I think it's kind of important to consider free fall problems separately from the other motion problems. But eventually, I think you'll come to see that they're very similar in the way that you approach them and the way that you do the algebra to solve the problem for the specific answer that they're asking for. Let's go over this specific term, free fall. What are we actually talking about when we designate a problem as a free fall problem? Well, a freely falling object is an object that is falling under the sole influence of gravity. Under the sole influence of gravity. So that is the key piece of information when we're describing an object that is in free fall. If it's only under the influence of gravity, the sole influence of gravity, that means that the Earth's gravitational force is the only force on the object. Notice that I referenced the Earth. Most of our problems, when objects are falling, will take place on the Earth. Objects can fall other places in the universe, and they will be subjected to other gravitational pulls, and they could be said to be in free fall in those other locations. But most of our problems are going to take place on Earth, and so we will be considering the force that is the Earth's gravity. But again, the key idea here is that gravity is the only force on the object. So if an object is in free fall, it means basically that we are ignoring air resistance. So freely falling objects do not encounter air resistance. Okay? Now that is not a realistic scenario. So free fall is kind of an imaginary state of physics to consider. Something like a frictionless universe. You know, if you were considering what the world would be like without friction. Well, that's not a real scenario. That's not something that you can consider in real life. And free fall is a little bit like that because objects do encounter air resistance as they fall, unless they fall in a vacuum. So you could remove the air, in which case you would have a real life free fall situation. Most of the time we consider that an object is in free fall because gravity is such a large force in comparison to the air resistance that most objects feel when they fall, so the force of air resistance can often be ignored. And so if we are ignoring the force of air resistance, then the object is said to be in free fall. So moving on to this second sentence here, any object that is being acted on only by the force of gravity is said to be in a state of free fall. And there are two important motion characteristics that are true of all free-falling objects. And we've already talked about the first one. That is, if gravity is the only force on the object, then we must not be considering air resistance. So these freely falling objects are not experiencing air resistance, so there either is no air or the air resistance is so small that we're ignoring it. And second, all freely falling objects on Earth accelerate downward at a rate of 9.8 meters per second per second. Now this value is an acceleration. See this set of units, meters per second per second? That set of units has meters per second in the numerator, those are velocity units, and seconds in the denominator. Those are time units. So this is the rate at which the velocity changes. And this is how we defined acceleration the other day when we were talking about it. We said that we would collect together those seconds that are in the denominator and write that as meters per second squared. So if an object is falling on Earth, its acceleration will be 9.8 meters per second squared downward. Now, that's a little confusing because it doesn't actually mean that the object has to be moving downward, but the acceleration is always in the direction of the force, and the force of gravity is always downward, so the acceleration is downward. Now, what we mean by that is if the object is falling downward, then it will be speeding up by 9.8 meters per second every second. If it's moving upward, then it will be slowing down. It will be slowing down by 9.8 meters per second every second. So when we say the acceleration is downward, that can be a little confusing because it doesn't actually mean the motion is downward. Acceleration always has the same direction as force. The force of gravity is downward, so acceleration is also downward. But that doesn't mean the object has to be moving downward. If it's moving downward, it speeds up. If it's moving upward, it slows down. Now, that's going to be more important to us later as we consider free fall and gravity together in Unit 3. But for now, we will be using this value, 9.8 meters per second squared, to indicate the change in velocity for an object as it falls. Sometimes it will be convenient for us to approximate the value 9.8 and only give it one significant figure because it's so close to 10, and 10 is such an easy number to do math with that sometimes it's convenient to approximate the value 9.8 as 10, and it's easy to add 10 or subtract 10, multiply by 10, divide by 10. You won't be doing that in your free fall problems on Motion Worksheet 3. You will be using the more correct value of the acceleration, 9.81 meters per second squared. At sea level, the acceleration caused by the Earth's gravity, I think, is something like 9.8066, and it goes on and on as we measure more and more carefully. So this third significant figure or second decimal place value in the hundredths place is a 1. Okay, one last thing before we talk about the problem solving piece, and that is that it's key that you remember that acceleration is not velocity. So when we say that the acceleration is constant and the same for all objects, we're absolutely not saying that the velocity is constant as an object falls. The velocity of an object will speed up as it falls, and this number is telling you how it speeds up. Every second it increases by almost 10. So if I drop an object and its initial velocity is 0, 1 second later its velocity will be about 10. Another second later its velocity will be about 20. Another second later its velocity will be about 30. Its velocity is changing by about 10, in reality 9.81, meters per second each second. So this value isn't telling you the velocity. Again, acceleration tells you how the velocity changes in a regular manner each second. Okay? All right, a few other things before you start your own problem solving and possibly look at the other example videos. Free fall problems are motion problems. They're motion problems like the other motion problems that you have been solving on motion worksheet 1 and motion worksheet 2 and motion worksheet 3. They use the same set of variables: the displacement, delta x, the time, the initial velocity, the final velocity, the average velocity, the acceleration. The thing that makes the free fall problem different is that the acceleration is known. Since the acceleration of an object in free fall is 9.81 meters per second squared, all they have to do is tell you that the object is falling, and you will automatically know what that acceleration is. Oops, sorry. You will automatically know that that acceleration is 9.81 meters per second squared. So see how none of these problems said that. A stone is dropped from a cliff. How long does it take? A diver in Acapulco, Mexico leaps from a point 36 meters above the sea. What's the diver's speed as he hits the water? Passengers on the Demon Drop are in free fall for 1.5 seconds. How fast are they going? How far do they fall? A water balloon is dropped from a third-story window 9.15 meters above the ground. How long does it take? How fast is the balloon going right before it hits the ground? Nowhere in those problems did it tell you that the acceleration was going to be 9.81 meters per second squared. But because those problems are in the free fall section, and because you know that when an object is dropped and it falls on Earth, it will always have the same acceleration, you get to put that number in even though it's not explicitly stated in the problem. The other thing that's typically not stated in the problem is the initial velocity. And the initial velocity is implied by the word dropped. But even then, sometimes that language is not used. So, for example, in problem 14, a stone is dropped. Imagine something being dropped. You're holding it. The velocity of the object is 0, and then you let it go, and it starts to fall and it starts to speed up. And so its initial velocity is 0 from when you were holding it. So using this term is dropped, using that phrase, implies that the initial velocity is 0. But in all honesty, the initial velocity is 0 in essentially every free fall problem, whether it says the word dropped or not. So in number 15, a diver in Acapulco, Mexico leaps from a point 36 meters above the sea. The driver's not dropped, and yet we're going to assume the initial velocity is 0. Passengers on the Demon Drop at Cedar Point, Ohio are in free fall for 1.5 seconds. See how in this problem it does say, assuming they start from rest. That means the initial velocity is 0. In number 17, a water balloon is dropped. So in these 4 problems, the initial velocity is 0. And the initial velocity is almost always 0 in a free fall problem. Now, it doesn't have to be. You can throw an object downward. You can give it an initial velocity that's not 0. That's just not typically the way these problems work. So if I throw an object down and I give it an initial velocity of 10, 1 second later it's going to be going 20, and another second later it's going to be going 30, and another second later it's going to be going 40. Now I'm approximating. I'm using 10 instead of 9.81. But I think the point is clear. Every second the speed increases by about 10 meters per second. Typically the initial velocity is 0, but it doesn't have to be. It probably will be, though, in most of your problems. So the initial velocity is 0. Sometimes that's stated. Assume it starts from rest. Sometimes it's implied. The object is dropped. Sometimes it's not stated or implied, as in number 15, where the diver leaps from a point 36 meters above the sea. But we assume the initial velocity is 0 to simplify the problem. Not only do these problems use the same set of variables, they're motion problems, so they use the same set of equations. These problems don't have to be separate from the rest of the motion problems. I separate them from the rest of the motion problems when you're first learning how to do them, so that we can talk about how the acceleration in each of these problems is 9.81 and how the initial velocity is 0. Usually, when you are solving these problems, you will be asked, how long does it take to fall? You will be finding the time. Or, how far does it fall? You will be finding the distance. Or, how fast is it going after a certain amount of time or after it falls a certain distance? I have solved some sample problems that follow those specific routes in subsequent videos. So here's what I think you should do. As this video wraps up, you basically have all the information you need to solve these 4 problems and other motion problems. But if you get stuck on any of them, there are sample problems that are solved for you that will help you to solve these. So the next video, video number 2, shows you how to solve for displacement. How far does it fall? So number 16. Passengers on the Demon Drop at Cedar Point, Ohio are in free fall for 1.5 seconds. Assuming they start from rest, what is their velocity after 1.5 seconds and how far do they fall? So if you want an example problem for how far do they fall, that's in video number 2. The third video shows a sample problem for how long does it take. So number 14, how long does the stone take to fall? And number 17, how long does it take for the balloon to fall? So if you're looking for a sample problem in order to find the time, that's going to be in video number 3. And then the fourth video is how fast. How fast is it going after this amount of time? Or how fast is it going after it falls this far? So that's like number 15. What is the diver's speed as he hits the water? You're solving for final velocity there. Or in number 16, assuming they start from rest, what is their velocity after 1.5 seconds? Or in number 17, how fast is the balloon moving right before it hits the ground? So in those problems, you're trying to find the speed, and you can check that out in the 4th video. I did not anticipate making a 5th video, but I did make a 5th video, and that one is about solving a problem where the acceleration is caused by gravity, but the object's not falling on the Earth, so the gravitational acceleration isn't 9.81, it's falling on the moon, so it has a different gravitational acceleration. That's another sample problem. It doesn't help you solve any of these specifically, but I thought that that was something to consider. What if the object is falling in a location with a different gravitational field? All right, there's your introduction to free fall problems. As I've already said, the next set of problems show a specific problem being solved for a specific variable. The next one shows you how to find the displacement. The one after that shows you how to find the time. The one after that shows you how to find the velocity. Okay, good luck.